Hey guys, welcome to your intro to covalent bonding. We spent our last unit talking about ionic bonding and metallic bonding, and now it's time to move on to covalent. So I want you guys to remember, and this is not yet in your notes, although we will be taking notes on pages 2 and 3 throughout this PowerPoint. Please remember that the reason why substances form bonds in the first place is to hold two atoms together in order to create a compound. And this process adds stability to these atoms. Like they are trying to obey that octet rule that makes two atoms more stable together than they would be alone. And when that happens, this force that is created is called a chemical bond. And we learned that there are three main types. Ionic, where electrons are transferred from a metal to a nonmetal. And metallic, which is that sea of electron structure that holds together either samples of a pure metal or samples of an alloy, a mixture of metals. But while ionic resulted in a transfer of electrons to achieve this octet rule, covalent bonding is when there is a sharing of electrons to achieve that full valence shell. So here's your first definition. A covalent bond is a chemical bond that results from the sharing of valence electrons. And as always, if this is too fast, go ahead and pause where you need to go ahead and take your notes. So let's sum this up in a chart. Covalent bonds are formed between nonmetals. So whereas ionic was a metal to a nonmetal, covalent bonds are a nonmetal to a nonmetal with mid to high electronegativity values. Remember, that means that they love electrons. And if both of those nonmetal atoms love electrons and attract electrons strongly in the bond, no one is going to be ready or willing to give away a valence electron, like the metals were in an ionic bond. This sharing of electrons achieves the octet that is needed for stability. And in fact, what actually ends up happening is the individual atomic electron orbitals overlap to create these new areas of probability between the atoms where the electrons can now exist. These are called molecular orbitals or bonding orbitals, something that we're going to learn about in AP chemistry. Here is where we finally get to use that word molecules. Remember, when we're talking about ionic compounds, we use the word units or salts. And here we get those interesting molecular shapes and we call them molecules. Water being obviously a very important example of a covalent compound for us. Hydrogen, a nonmetal. Oxygen, also a nonmetal. Going to have to share electrons between them in order to form that compound. Now, let's take a look at two examples of the formation of covalent bonds. Now, these two examples that I'm going to show you are between atoms of the same element. It does not have to be atoms of the same element, as we just saw with the hydrogen example, with the water example, where we have both hydrogen and oxygen coming together to form a compound. So these next two examples are atoms of the same element, which is something that can happen, but again, they can be atoms of different elements sharing electrons. The key is the sharing of the electrons. So if we look at this Lewis dot diagram of one fluorine atom, we see its 7 valence electrons, with one more electron needed in order to satisfy its octet. What if we had a second fluorine atom present with its 7 valence electrons? Do you see how the unbonded electron from one fluorine, or the unpaired, I should say, electron from one fluorine matches up perfectly with the unpaired electron in the other fluorine? That overlap right there in our Venn diagram, those two shared electrons, is what we call a single covalent bond. That's the bond. It's just when the electrons exist between the nuclei of those two atoms, and they share. So now if we were to count how many valence electrons each fluorine atom has, as we count 1, 2, 3, 4, 5, 6, shared 7, 8. I can also count those two when I'm counting up my valence electrons for the other fluorine. 1, 2, 3, 4, 5, 6, 7, 8. And so now both of my fluorine atoms have 8 valence electrons. And this is how we represent that in an actual Lewis dot diagram drawing. In between, that shared pair is drawn as a single line. That is your single covalent bond. Electrons that are not shared are called lone pairs, or sometimes they are called unshared pairs. And when everybody is satisfied and we understand what the molecule is composed of, we write a molecular formula. And just like with ionic formulas, we use subscripts to indicate how many of each atom exist in the compound. Let's look at another example. Let's say I have an oxygen atom. Oxygen has 6 valence electrons, as you can see from that diagram. If I bring in a second oxygen atom, I can see its 6 valence electrons and an overlap here. This overlap of valence electrons between the oxygens is creating a place for a bond. However, neither oxygen is yet satisfied with 8 valence electrons. Now, each oxygen has 7. 1, 2, 3, 4, 5, 6, 7. I can count those two again for the other oxygen. 1, 2, 3, 4, 5, 6, 7. So maybe some of you can see what's going to happen here. But in order to get to 8, how convenient that we have 2 other electrons that are also available to be shared because they are unpaired electrons. And that's exactly what happens. If we just redraw that structure as those lone electrons being a shared pair, we now have 2 shared pairs between the oxygens. And if that's the case, if 4 of my pairs are shared and 4 are lone, now I have an octet, both for the oxygen on the right and the oxygen on the left, and everybody's satisfied. We would draw this as 2 lines, indicating a double bond. And again, our lone pairs or our unshared pairs, and it doesn't matter where they go on the diagram, and we're going to do some rules for drawing Lewis dot diagrams later. Just wanted to kind of give you guys a teaser about what these molecules look like and how they're very different than the crystal lattice structure that we showed forming for ionic compounds. And of course, the formula for this molecule is O2. Now, if there's such a thing as single bonds and double bonds, then you might guess that yes, there are also triple bonds. So let's take a minute and look at the different types of covalent bonds. A single bond has 1 shared pair of electrons and is represented by a single line between the atoms. Single bonds are generally the longest of the bonds. Now, of course, this will be made a little bit more complicated when we consider the atomic radius of each atom involved in the molecule. But generally speaking, if we are comparing atoms of the same size, single bonds will be longer than double bonds and triple bonds. A double bond is composed of 2 shared pairs of electrons, as we saw in the oxygen example, 2 lines, and they are shorter. If 3 pairs of electrons are being shared, that makes a triple bond, and that is the shortest. Now, one thing I would like you guys to note on the side of your chart here is that as you decrease in length and the bonds get shorter with more and more shared pairs between the atoms, with this decrease in length, you get an increase in strength. So as those atoms are held tighter and tighter together, the amount of energy needed to break that apart would increase the shorter and the stronger the bond. Which leads us to a conversation about bond dissociation energy. That's just a fancy word for how much energy you would need to put in to break apart two covalently bonded atoms. We measure this in kilojoules, joules being a unit of energy, kilo being 1,000 joules. Do you guys remember what we called this in ionic bonding? The energy needed to break apart the crystal lattice structure of an ionic compound? We called it lattice energy. Lattice energies are much bigger, much bigger than bond dissociation energies. Ionic bonds are much stronger than covalent bonds because that electrostatic force, the attraction of a positive to a negative, is one of the strongest forces in nature. And it is a much stronger force than the attraction of shared electron pairs between atoms. Okay, and moving on finally to properties, and then we will talk naming. Covalent compounds, because they do not have a crystal lattice structure, and because they can have many different geometric shapes, they have a wide range of properties. So when we were talking about ionic compounds, their properties were pretty standard and straightforward, ionic compound to ionic compound. You know, they're solids, they're typically white, they're strong in terms of high melting and boiling points, but they're brittle and not malleable. They're conductive in water. You know, they had very standard properties. Because covalent compounds have lots of different molecular shapes, they're going to have lots of different properties depending on what substance you're talking about. So as you can see, they range from solids to liquids to gases. Like ionic compounds, almost always solid at room temperature. Covalent compounds can be solid, liquid, or gas, depending on which one we were talking about. Compared to ionic compounds, they have low melting and boiling points. Much easier to melt and boil covalent compounds than ionic compounds. And they are relatively not conductive. So remember when I did that conductivity test in water, which is just plain old covalent, you did not see that light bulb light up. However, when I submerged the light bulb in the water, the covalent compound, with an ionic salt dissolved in it, much more conductive. But of course, we do know that water has the ability to conduct electricity. So don't drop your phone in the bathtub or a hairdryer for that matter. Okay, moving on to naming. So I'm going to have you guys just jot down these naming rules, and then I'm going to pull up my whiteboard so I can do a couple of examples. Naming covalent compounds is super easy, especially compared to the naming of ionic compounds. These are probably ones you're already familiar with, and there's no worry about charges or balancing charges or Roman numerals, none of that. Here's what they sound like. All covalent compounds names sound like this: prefix, element, ide. The only prefix that we do not use is mono on the first element. Like if that first element, if there's only one of that atom, we just don't use mono on the first. If the second element has only one atom, we do use mono on the second. So it's sort of arbitrary. We don't use mono on the first element. All other prefixes are used to indicate how many of each atom is in the compound. And that's it. Oh, of course, a reminder about our Greek prefixes. So the same Greek prefixes that you guys used for naming hydrates: mono, di, tri, tetra, oh, spelling error, penta, not penna. That should be penta, you guys. Hexa, hepta, octa, nona, and deca. So those are the prefixes that we are going to use when naming these covalent compounds. So I'm just going to pause this for a second and switch over to my whiteboard. Okay, you guys, so I know I didn't give you a ton of room to practice. So if you have any room left over to sort of squish into your notes, a couple of examples of how we do these covalent names. All right, so we're going to go prefix, element, ide. And the only time we don't use a prefix is mono on the first. So here we go, N2O5, going to use my prefix for 2, dinitrogen. Don't change that first name in any way. Need the prefix for 5, penta. Now, I'm going to drop the A, so this is an interesting spelling thing. It's actually pent oxide. Okay, so there's no AO combinations. We drop those, okay? Also no OO combinations. If it was monoxide, we wouldn't do monoxide. We would drop one of the O's. So no AO, no OO. However, we do use double I's, which is interesting. That one is okay. This one, not okay. Don't do that. This one, not okay. Don't do that. Listen, I'm not going to ding you on the spelling, but try your best. Okay, here we go. Naming rule. Prefix for your first element. This is a 1, so we're just not going to use the mono. Carbon. So the mono on the first is understood. We do need the mono on the second. Monoxide. There's that monoxide example where you would not write monoxide. You guys all know this one. Carbon dioxide. And let's see if we can go in reverse. So here's my name, nitrogen trihydride. That must mean 1 nitrogen because there's no prefix. Hydride is my element hydrogen. 3 of them. Diphosphorus, it's 2 phosphorus atoms. Hexabromide, bromine, and 6 of them. So very, very simple to write names and formulas for covalent compounds. Prefix element, ide. And the reason why we use these prefixes in covalent naming, but we did not use them in ionic naming, is because in covalent naming, you can have 2 different versions of a carbon-oxygen-based compound. In fact, you can have many more than 2 versions of it. In an ionic compound, there is no other way to combine magnesium and chlorine. It has to be MgCl2 because the charges have to cancel out. And so this is why the formula is that. And so we don't need prefixes to tell us how many of each atom are in the compound. But in covalent compounds, because there's lots of different ways for the electrons to be shared by single bonds, by double bonds, by triple bonds, we're going to have actually different compounds forming out of the same elements. And that's the reason why we need to use prefixes in those names to tell us how many of each element is present. And that's it. You have completed your intro to covalent bonding. Great work.